In this video, we're going to look at a function of two variables. We're going to identify all the critical points, which are the points where the gradient of f equals the zero vector, or the first partial derivatives equal zero. And then to follow that up, we're going to classify the critical points by using the second derivative test, which is that d value covered in an earlier video. The first step then is identifying what the derivatives are. So we do a scan down here, and we find the x derivative here would be 6xy minus 6x. The y partial derivative would be 3x squared plus 3y squared minus 6y. And then we set those equal to 0 to find the critical points. In these kinds of examples, the most effective procedure is to factor these forms. There's no way to isolate one of the variables easily. So if we factor this, we can bring out a common 6 and x, and then we get y minus 1. And in this expression down here, we can divide through by 3, and that's about all we can do. We'll have x squared plus y squared minus 2y equals 0. Label our equations, and then use your skills entirely from high school previous classes for solving a set of nonlinear equations. Now, equation 2 is challenging to work with. It's hard to isolate. We can isolate x, but it'll give us a horrible square root thing. However, the factored form of equation 1 gives us a lot to work with. Specifically, equation 1 tells us that there are exactly two possibilities. Either x equals 0 or y equals 1. To satisfy that equation, we have to have one of those two pieces in play. What we can then do is take each of these and use them in 2. So if we take x equals 0, substitute that into equation 2, then we get 0 plus y squared minus 2y equals 0. And that, without the x now, because the x was equal to 0, we can factor, and then we get a nice form here, which is y equals 0 or y equals 2. All right, so from the first equation, we set x equal to 0 as one possibility. Then we got two solutions out of that, and that gives us 0, 0 then, x and y, and the point 0, 2 as critical points. And that is an excellent start to our search. Next up, we go back to the other trail. We had x equals 0, we've investigated that. The other possibility is y equals 1. If we take that and use that in equation 2, then we'll have x squared plus 1 minus 2 equals 0. And that translates to x squared equals negative 1 on this side, turns to plus 1 on that side. That'll give us x equals plus 1 or minus 1. Well, that leads to x equals 1, y equals 1. 1, 1 is a point. X equals negative 1, y equals 1 as another critical point. And so in total, we have 4 critical points out of this entire search. And that is the first part of our question. We've identified all of the critical points. Our next step is to classify the critical points using the second derivative test. Well, if we are using the second derivative test, we'd better have the second derivatives. So here we would go back a page, take a look at the x function here, the x derivative with one derivative, and differentiate it again with respect to x. That'll give us 6y minus 6. We would then have the y double derivative. That's taking the y derivative of this expression, which will actually be 0 plus another 6y minus 6. That's interesting. More convenience because of the function that we picked. This is not a general rule. And last but not least, if we start with the one x derivative and then take the y derivative, we will simply end up with 6x. And we can confirm that going back a page. If we take the x derivative of this, we would have 6x and there's no x's here, so just 6x again. That's what we're saying for the mixed partial derivative. That is perfect. All right. Remind ourselves of the formula for the second derivative test. What we're going to need to do is evaluate these products minus that squared for all of the critical points. So this is usually best done in a table, just so we can organize our procedures. Going back, our critical points were 0, 0, 0, 2, and 1, 1, and negative 1, 1. We can then calculate each of the second derivatives for each of those points. So what we're going to do is take these values, put them in the formulas, and then fill in these three columns. At the point 0, 0, the x second derivative will be 0 minus 6, which is negative 6. At 0, 0, the y derivative will be the same. And last but not least, the mixed partial will be 0. Next point, at 0, 2, so this is the y value. We will have 12 minus 6, that'll be positive 6. And it's the same formula for the y second derivative. And last but not least, we have 0 for x, so that is 0. Next critical point, we have 1 times 6 minus 6. That's going to be 0. Same thing for fyy, it's the same formula. Last but not least, we'll have 6 for the mixed partial. And our final critical point, x is negative 1, but y is 1. So we'll have 6 minus 6. This will be 0 again, 0 again. And then for this one, it'll be negative 6 for the mixed partial derivative. With that, we can then take the calculation for our d value, take this times this minus this last column squared. That's just using the formula up here. And that will give us 36 minus 0. That will give us 36 as well. This will give us 0 minus 36. And this is squared, so it becomes positive. And then we subtract it. So this is also negative 36. Then we apply the classification of these values, just looking at the signs. This value is negative. That implies a mix of concavities. Think of this d as a product of the two concavities. If we have a mix of concavities, then that means it is a saddle point. And for exactly the same reason, this is also a saddle point. These values are positive, and so they're a little tougher to tell apart. What that tells us is that we have the same concavities, but we don't know just by looking at that one value whether they're both positive or both negative. So then we go back to here, and we see that fxx is negative, which is concave down. Well, imagine a point where we have zero gradient or a flat tangent plane, and it's concave down nearby. Well, that's going to be a local max. Now, what about this point here? Here we have fxx is positive, which is concave up. Well, if something's concave up at a critical point, it's going to be a local minimum. And there we are. We've classified all 4 critical points of this function. It's also worth noting that the procedure we followed of starting with our function, taking a derivative to identify critical points by setting it equal to 0, looking at the second derivative values, specifically the concavity, this is very similar to what we did with single variable calculus. One last important note, what we've identified here are local maxes and local minima. Saddle point is neither. A follow-up question might be whether those local max and mins that we found are also the global max and global min respectively. Take a moment to look at this function and ask yourself if that would be the case. Pause the video and then we'll check in. The answer here would be a strong no. Remember, we've seen earlier in the course that if a function in any direction might have a local max, but if it can go up towards infinity, if our function approaches positive infinity in some direction, then that means there cannot be a global maximum. What we found can be a nice local maximum, but there's no single highest point on the function as a whole. And if we scan down the list of terms here, we can imagine having x equals 0 or constant, it doesn't really matter. And as y goes towards infinity, our function is going to get larger and larger and larger and larger and larger. So f is going to go towards positive infinity, so no global max. And the cubic function is handy that way because we can also let y go to negative infinity. And if that's the case, when we take a negative large value and cube it, we're going to get another negative large value. That's going to approach negative infinity as well. And by exactly the same logic chain, there cannot be a global minimum on this function either. So we found local maxima and min, but they are not, in this case here, the absolute highest or absolute lowest points for the function.